Bismillah, fourth lecture from the series of basic econometrics course. In the previous lecture, we already discussed the concepts of population regression function, the sample regression function, and the meaning of term linear and stochastic significance of stochastic error term. So all these concepts we already discussed in the previous lecture. So in this lecture, our contents will be the method of ordinary least square, assumptions underlying the method of least square. So let's get started from the concept of method of least square. Basically, method of least square is a statistical technique used in econometrics and other fields of to estimate the parameters of a linear regression model. So OLS is widely used in regression analysis to understand and quantify the relationship between the variables and to make the prediction based on these relationships. So if you look at the concept of uh, relationship between the two variables, so if you write this one, yt is a dependent variable and that is depend on the x variable, that is alpha plus beta xt. So you have to focus on the relationship between the two variables. So if x increases or decreases, what will be the impact on y? This is basically is a regression. In this lecture, we have to calculate the values of alpha and beta that are estimated values, alpha hat or alpha cap and beta hat. So if you look at the diagram, this diagram is basically a sample regression function. So these are the estimated values of beta 1 hat and beta 2 hat. So this regression function, sample regression function, represent the population. So these values are close to the parameters of the population. So if you look at the mu1, mu2, mu3, and mu4, these are residuals. So we can say that, so error term is basically mu I is a difference between y minus y hat. So that's the difference between actual and estimated value. So in this ordinary least square method, we have to minimize the error, and we can derive alpha cap or alpha hat and beta hat by optimal solution or by applying the first order condition. So we can write this one by minimizing rule. So summation mu I square is equal to summation by applying the summation. So y minus y hat. You can say y hat is equal to alpha hat plus beta hat x. So by putting the value of y hat in the following equation, so summation mu I square is equal to, you can write it square. So summation y minus alpha hat plus beta hat x whole square. So summation mu I square is equal to summation y minus alpha hat minus beta hat x whole square. So by applying first order condition, so we take partial derivative with respect to alpha hat and beta hat. So by taking the partial derivative with respect to alpha hat, we can write it as 2 by applying the power rule. Summation y minus alpha hat minus beta hat x into -1 and put it equal to 0 according to first order condition. So we can write it as -2 summation y minus alpha hat minus beta hat x is equal to 0. By dividing minus 2 on both sides, then you can write it as summation y by applying summation inside the bracket. So summation y minus. So if you put the summation with a constant, then it will become n. So n alpha hat minus, because summation must be applied with the variable. So beta hat summation x is equal to 0. So you can write it as summation y is equal to n alpha hat minus, plus beta hat summation x. That is normal equation 1. If you take the derivative, partial derivative with respect to alpha hat. So now we take the partial derivative with respect to beta hat. So we can write this one like partial derivative with respect to beta hat. We can write this one 2 summation y minus alpha hat minus beta hat x into minus x is equal to 0. So we can write it as minus 2 summation y minus alpha hat minus beta hat x into x is equal to 0 by dividing with minus 2 on both sides. So equation will be like summation. So if we multiply x inside the bracket, so you can write it as xy minus alpha estimated x minus beta estimated x square is equal to 0. So by applying summation inside the bracket, so you can write it as summation xy minus alpha estimated summation x minus beta estimated summation x square is equal to 0. So you can write it by rearranging the equation. You can write it like summation xy is equal to alpha estimated summation x plus beta estimated summation x square is equal to equation number 2. So you just make the two normal equations. So by solving these two equations, you can write it as like by comparing both alpha equation 1 and equation 2, and by cancelling method, we can derive the value of beta estimated. So by this, we multiply equation 2 by n. So you can write it as n multiplied by equation 2. So if you multiply equation 2 by n, then you can write it as n summation xy is equal to n alpha estimated summation x plus n beta estimated summation x square. Then multiply equation 1 by summation x to compare for comparing the both equations. So and subtract from equation 2. So we can write it minus equation summation x multiplied by equation 1. So you can write it as summation x summation y is equal to n alpha estimated summation x plus beta estimated summation x whole square. So by subtracting this equation, minus, you can write it minus and minus. So if we compare this, you can cancel out this one. So you can write finally n summation xy minus summation x summation y is equal to n beta estimated summation x squared minus beta estimated summation x whole square. So you can write it as it is n summation xy minus summation x summation y is equal to, by taking common beta, so you can write it beta hat is equal to into n summation x square minus summation x whole square. So by dividing on both sides by this n summation x square minus summation x whole square, so you can see n summation x square minus summation x whole square, that is a value of beta estimated. So beta's a hat. So if you look at the equation number one, normal equation number one, that is summation y is equal to n alpha estimated plus beta estimated summation x. N alpha estimated plus beta estimated summation x. This is the normal equation number one, as we derive from by minimizing rule. So by dividing n on both sides, you can write it n. And we know that the mean value of y is equal to summation y beta n, and x bar is equal to summation x beta n. So you can write it y bar is equal to n cancel out by n. So alpha estimated plus beta estimated x bar. So you can rearrange this equation and derive the value of alpha estimated. So you can write it y bar minus beta estimated x bar is equal to alpha hat. So these are the parameters, estimators, and that are the true estimators. So if you look at the formula of alpha and the formula of beta that we already derived in the previous slide, so beta estimated is equal to n summation xy minus summation x summation y over n summation x square minus summation x whole square. So if you are given the data of x and y, then you have to derive the values of alpha estimated and beta estimated. So these are the concept of the estimators, so that we can check out by taking the by applying the OLS method. So this is all about the a method of ordinary least square method, and these are the true estimators. Alpha and beta are the true estimators. So now we start from the properties of estimators. So OLS estimator, what are the properties of OLS estimators? So OLS estimators basically because on the behalf of the values of X and Y, so they are easily computed. They can be easily computed. So OLS estimators, if you are given the values of X and Y, and you have to find the values of alpha and beta estimated, then by applying the ordinary least square method, you can easily compute the values of alpha and beta. So the second property is that they are point estimators. So you can represent the whole population on the behalf of the sample estimators. So they already we already explained this one by the regression line. We can say that this is our regression line. These are deviated values. So this line is basically show the combination or locus of the points of the mean values, the X and Y mean values. So this is derived from the sample. So that represent the whole population. So this regression line basically has some own properties, like this line passes through the mean values. As I said before, so the mean values. This is a combination of mean values. This is X bar, and this X, suppose X1 bar, X2 bar. This is Y1 bar. This is Y2 bar. So second property of this regression line is that, so the mean value of estimated Y is equal to Y hat. So actual value, that is Y, and that will be equal to the Y hat. So there's no concept of error. So the mean value of residual UI is equal to 0. So in this line, we expect that the expected value of mu I is equal to 0. So the fourth property is your mu I, that is error term, is uncorrelated with the Y. So your error term mu I will not correlate with the dependent variable. So another is residual mu I is uncorrelated with the X variable. So these are some properties of regression line. So on the behalf of regression line, we can explain the true estimators of alpha and beta. So now we will discuss about the assumptions of that is assumptions for underlying the method of least square. So there are several assumptions. So we will discuss in this lecture. So first assumption is that the regression line or regression model is linear in terms of parameter, though it may or may not be linear in terms of variable. As I said before, this is our econometric model. So this is alpha plus beta xt plus mu t. So this is error term. So in the meaning of this assumption is that our regression model will be linear in terms of parameters, though it may or may not be linear in terms of variable. If you look at the relationship between the two variables, like if we are studying the method of least square or classical linear regression model, and we have to define the linear relationship, then if these variables have positive relationship, then you can say that this is a regression line. So it is not compulsory our regression line must be linear. It may be non-linear, like if you look at the cost functions. So that is average cost, this curve is non-linear. If you look at the other cost curves, then in economics, the variables not must be linear. They may or may not be linear. So it depend on the relationship between the two variables. So in the previous example, as I said, so in the environmental Kuznets curve, so the relationship between GDP and CO2 emission is like this. So when GDP increases, the CO2 emission will also increases at the initial levels. So, but at the peak or at the optimal level, that is when CO2 is maximum and GDP and after this point, this is threshold point. After this point, your GDP will increase, but your CO2 emission will decrease. This is basically the concept of environmental coordinate curve that I said before, and I already discussed the concept of environmental coordinate curve in detail in the previous lecture. So in this lecture or in this assumption, we just explain over parameters like alpha and beta. They will never be non-linear. So it's not possible the value of alpha and beta is insecure. So X maybe is insecure, but alpha beta will be linear. These parameters will be linear. So second assumption is that X values or X fixed X values or X values independent of error term. So it is assumed that our X values will not correlate to the error term. It means X values have no correlation with the error term mu I. So if our observation correlated with the error term, then our results will not be unbiased. So our result will not be blue, best linear unbiased estimators. So this is assumption. So the third assumption, so X, the mean value of X or expected value of random disturbance term mu I is equal to 0. So it is assumed that our expected value of error term is equal to 0. It means if error term is equal to 0, then our actual y must be equal to estimated y. So this is an assumption, all about the assumption that our expected value of disturbance term, that is random disturbance term, this is the expected value will be 0. Next assumption is homoscedasticity or constant variance of error term mu I. Homoscedasticity or constant variance of error term. The variance of error term or disturbance term is the same regardless of the values of X. So if you look at the two diagrams, in this diagram, you can see X1, X2, and X3. So these variances are same. So, but in the second diagram on X1, X2, and X3, this variance already changed. So for this, we can say that that is homoscedasticity. So, sorry, heteroscedasticity. So for this, we can say this is homoscedasticity because the variance between the error terms is same. But in this case, in heteroscedasticity, this is changed. So the fifth assumption is so no autocorrelation between the disturbance term. So we can say that the error term ui and uj do not correlate to one another. So if they correlated, then problem will arise. That is called autocorrelation. So if you look at the diagram, so this is mu I positive. This is mu I negative. This is mu I positive y-axis. This is mu I negative. So if the relationship between the error term is like this, so we can say that this is positive associated. If the relationship was this is mu I positive, mu I negative, mu I negative, mu I positive. So if the association between two error term is like shows like this type of scatter plot, this shows a negative association between the two error terms. So if This is 4-quarter diagram. Mu I negative, mu I positive, mu I positive, and mu I negative. So if the relationship between two error terms is like ui and uj is like this, so that shows no autocorrelation, no serial correlation between the disturbance term. So if error terms move like this, then we can say that these error term in time period, I time period, and error term in the j time period correlated in positive way. This is correlated in negative way, and this in this diagram we can say that error term the correlation between the two error terms is 0. Next assumption is the number of observation and must be greater than the number of parameters to be estimated. It means that over alpha and beta, suppose we have in the simple regression model, so yt is equal to alpha plus beta xt, so plus mu t score. This is our simple regression model. So in this model, we have parameters alpha and beta, and we have variables y and x. So this assumption is basically is about that the values of x and y must be greater than the values of alpha and beta. It means if we have alpha and beta 2, then x and y must be, number of observation must be greater than 2. Then it will be possible for the econometrician to estimate the relationship between the two variables x and y. So if the number of observation is greater than the number of parameters. So in the second and the seventh assumption, we can say that the value of x must not be same. So it means x have variation, x variable will change. It means if we look at the schedule, suppose x value is 1, 2, 3, suppose 4 and 5. So suppose against this x, we have y values 2, 6, 9, 10, suppose 20. So we can see that x has some variation. X is not same. If x is same throughout the time period, then it's not possible to check the relationship between x and y. So it is assumed that x have some variation, or x values is not same throughout the sample. So these are some assumptions, and last two assumptions are explained in the next chapter, but I explain these assumptions together. So no exact collinearity between the variables, that is assumption number 8. So it means two variables do not associated do not have collinearity between two variables. It means your variable x1 and x2, suppose these two variables, if associated in strong way, the association between the two variables is very much high, that leads to the biased results. So it means if you look at the diagram, Venn diagram, suppose this is x and this is y. So the relationship between x and y, suppose these are some independent variables, like suppose this is x1 and this is x2. So association between these two variable is shown by a Venn diagram. If you look at the second diagram, you can see this is x1, this is x2. So this is association between the two independent variable. So as compared to this, this diagram shows that x1 and x2 associated in strong way. So they have more association as compared to this equation. So if your variable are associated, independent variables are associated, they have strong association between them, then that leads to the problem that is multicollinearity. So multicollinearity is a problem that shows your independent variable, if associated in very much way, or they are associated in, they have strong association between them, then overall performance shows R square leads to a very high value. That show, apparently the model shows that that is good fitted model, but it suffer from the multicollinearity problem. So that's why it is assumed that two or more independent variables do not correlate to one another. So last assumption is assumption number 9, that is there's no specification bias. The model is correctly specified. So it means if you have a model yt is a function of, suppose, x1, x2, and x3. So y basically is dependent variable, or x1, x2 are independent variable. So if we specify the model, so we have avoid to include the unnecessary variable or irrelevant variable in the model. So we have to avoid the problem of specification. So we must not include the irrelevant variable, and we must not exclude the relevant variable, or must will be careful about the specification of the model. So if we assume that model is specification bias, so it means no specification bias in the model. So if your model is must be correctly specified, so that model shows the relevance independent variables and have correct functional form. So this is all about the assumption number 9. So all these assumptions are for to getting the true estimator like alpha and beta. So in this lecture, we discussed the basic two concepts, what is OLS, ordinary least square method, and how to derive the values of alpha and beta. We already discussed and derived the values of alpha and beta, that are the true estimators. And in the next topic, we explain the assumptions of OLS, or classical linear regression model. So in the next lecture, we will explain the next topics.